Hello everyone, this is Orion's Brightest Star, and today we are going to be talking about parametrized curves and the inner product. So to begin, let's talk about parametrized curves. So a parametrized curve in Rn, that's basically the n-dimensional space of real numbers. So R3 would look like this, R3, R2 would look like this. So you might be familiar with the Cartesian plane, that's R2, and R1 would just be the real number line. So a parametrized curve in Rn is a smooth function, which let's call gamma, from I to Rn, where I, which is a subset of R, is an interval. So what precisely does that mean? Well, let's take a look. Let's make this R. Let's say that we have an interval I here, and we're trying to map it onto R3. So a possible parametrized curve might look like this, where this point is taken to this point is taken to this point is taken to this point. One metaphor that I think is particularly helpful when describing parametrized curves is that they're often used to describe particles in motion. For example, this might be, this interval right here might represent time, and suppose the particle is here at time 0, it might be here at time 1, it might be here at time 2. And the point is that it's not just like a regular curve, it has a parameter as well that gives it a sense of, as you will see soon, speed, and it might be analogized to time. So now that we have a basic definition about parametrized curves, let's talk about the derivative of a parametrized curve. So let's say we have a curve I to Rn, and it has components like so. What that basically means is that, let's give an example actually. What that basically means is if we have a parameterized curve with 3 components, each one might represent, say, the position in a given axis with respect to a given axis that the particle might have at a time t. For example, this is a very simple parameterized curve, but this would basically be the curve that looks like this, where this is the x-axis, this is the y-axis, and this is the z-axis. So at time 0, wait, I messed it up. It should be t, t, t. At time 0, we would have the position 0, 0, 0 right here. At time 1, we might have the position 1, 1, 1, and so on and so forth. So these components basically describe where a particle is relative to its given axis, x, y, z, or in the generalized case, we might label them by subscript. So anyways, that's a bit on components. So if we take the derivative of this, which we denote by this, that is the curve defined by this expression. Now, if we recall, this means taking the derivative of the function x1, so with respect to t. And of course, higher order derivatives are defined analogously. Now, throughout this series, I just assume that you know single variable calculus, because after all, as I mentioned before, differential geometry is using calculus to describe geometric properties of manifolds, but I will be, throughout, defining different concepts in multivariable linear algebra, just so nobody is left behind. So now let's take a look at our first proposition. The derivative of a curve at the time t in I, this epsilon sign basically means an element of. So if we think about it, if this is our interval I, t might be here. That's basically what it's saying. So the derivative is given by the formula gamma prime equals the limit as h approaches 0 Okay, so this is our expression that we propose. So when we ever have a proposition, we need to prove it. And here's how we're going to prove it. Let's take this expression right here. And what we're going to do is we're going to look at this in terms of components. So we have the limit as h approaches 0 of x1 t plus h, x2 t plus h, dot dot dot, xn t plus h, minus x1 t, x2 t, dot dot dot, xn t, and this is all over h. So we can actually simplify this further as the limit as h approaches 0 of x1 t plus h minus x1 t, because we're subtracting components together. That's how we subtract vectors. x2 t plus h minus x2 t dot 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 xn t plus h minus xn t. And this is all over h. So now we can, since h is a scalar, that is a number, we can divide each component by h. And what I mean by that is, instead of h dividing the whole vector, it's dividing each component. x2 t plus h minus xt over h dot 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 xn t plus h minus xn t over h. And if the limit can be carried over into each expression, and when we get that, we get a familiar formula. That is, we can represent this as x1 prime over t, x1 prime of t, because this is the formula for the derivative. x2 prime t and note that this is the definition of the derivative. So we've basically stated that this expression here is equal to this expression, which is the definition of the derivative. Therefore, our expression is equivalent to the expression for the derivative at time t in I. So let's talk a little bit about what the derivative actually means. So as you can see, the derivative is a vector. It has n components. And what we can say is that, let's say we have a curve in R2, and it goes a little bit like this. At this point, the derivative is going to be a vector tangent to the curve. That is, it's going to appear to have, it's going to look like it's touching the curve at like one point. It's not going to be like this. It's not going to be like, this. It's going to be in the direction of the curve. So if this is gamma, this would be gamma prime. But that's not all. The derivative has a specific magnitude based on the parameterization, which we call the speed. And the speed is basically what is called the norm of gamma prime. And the norm is also called the length, and it has a specific formula. So if we have the norm of this vector, it's the square root of x1 squared plus x2 squared plus dot 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 plus xn squared. That's basically the norm. So let me box that in. Furthermore, using an integral, we can calculate the arc length between t1 and t2. So that would just be the integral from t1 to t2 of the speed arc length would basically just be like the total length of the curve between t1 and t2, as in like total distance traveled. So now let's look at some more definitions. A curve is regular if its speed is non-zero. That is, and a curve is unit speed, or parameterized by arc length if its speed is always equal to 1. So that's basically a couple of definitions that you might find useful. And let's talk about, and you might be thinking, is every curve regular? And the answer is no. Because if we take a look at the curve gamma of t equals t squared, I mean, on the surface it looks like this. But if you differentiate it, you get this. This is simply by taking the derivative of t squared, which is 2t. And note that at t equals 0, the derivative is 0, 0. So over here, the tangent vector is 0. You can think of this as like, the particle is moving, it's slowing down, and it's stopped here. Of course, when you consider t equals 1, for example, it's moving at increasing speed. But over here, it's stopped. And that makes the curve irregular. Now, let's talk about the derivative. It might sometimes be called the velocity vector because the derivative of the position is the velocity. And you can think of a parametrized curve as the position. Furthermore, the second derivative is sometimes called acceleration for the same reason. Now we've talked a little bit about parametrized curves. Now let's discuss something called the inner product. So the inner product takes two vectors, we'll call them x and y, and let's say, sorry, x is x is represented by that, and y is represented by that. The inner product looks like this, and this is the formula for the inner product. So sometimes you might call it the dot product, and it looks like this. We're going to stick with this one because differential geometers tend to use that notation. Now the inner product has a couple important properties in terms of the real numbers. The complex inner product has different properties, so keep this in mind. We're only talking about real numbers here. So the inner product of two vectors x and y will be equal to the inner product of y and x. So it's symmetric. Now, if we have a scalar lambda, that is a number, plus another scalar mu, we have this formula. And it goes the same way for the other side. So x lambda y plus mu z is exactly what you would think it would be. Oh, that's y. Plus mu x z. So we call this bilinearity. Furthermore, we have that the inner product of a vector x with itself is the square of the norm. You can compare the formulas for the norm and the inner product, and you'll see this pretty clearly. And this equals 0 only if x is the 0 vector. That is, it's just zeros. Finally, we have that the inner product of x and y is less than or equal to the norm, or the absolute value of the inner product of x and y, which is less than or equal to the norm of x times the norm of y. Now, what does the inner product essentially mean visually? Let's say we have two vectors, x, oh this is badly drawn, and y, and there's an angle theta between them. The inner product of x and y is going to be equal to the magnitude of x times the magnitude of y times cosine theta, where theta is the angle. Now, you might note something. If theta is the right angle, that is x and y are perpendicular, cosine theta is going to be 0, and therefore the inner product of x and y would also be 0. That brings us to our next definition. X and y are orthogonal if, and you can think of orthogonality as like a fancy way of saying perpendicular, but we prefer the term orthogonal. And they are called parallel if x is a scalar multiple a scalar multiple of y, or if one is a scalar multiple of the other, without loss of generality. Now, we can also write a vector in terms of two parts. So let's say this is our vector x, and this is y. We can write it in terms of two vectors. There's one vector over here and one vector over there, and we're adding them together. Let's call this one that, and we call that one that. So, as you can see here, x is equal to this plus that. And this vector is parallel to y, and this one is orthogonal to y. We call this the projection of x in the direction of y. So if we have the formula projection equals, now this is the unit vector in the direction of y. So this is some random scalar, and this is the unit vector in the direction of y. We call this, which is the length of the projection, we call that the component of x in the direction of y. Now let's talk about orthonormal vectors. So each vector must be unit length, and each pair of distinct vectors must be orthogonal. So that might look like this. They're all at right angles to each other and they all have length 1. It could look like something else. So in other words, we have that, let's call them EI and EJ equals, and this thing is called the Kronecker delta. What that basically means is it's 1 if I equals j, and 0 if I does not equal j. So if you can represent any vector in terms of these orthogonal vectors, at least in the space you're working in, for example, if we have R3, we can represent any vector in terms of these three vectors, then we call the set of vectors an orthonormal basis. So that's a little bit of linear algebra knowledge. Let's move on to another proposition. Let's say we have two curves, gamma and beta, from I to Rn. If gamma has a constant norm, so let's say gamma t, the norm of gamma t equals c, then gamma t, or its derivative, is orthogonal to gamma t for all t in the interval. And you might be wondering, how is this possible? Let's prove it. So we know that the norm is c, therefore the derivative of this expression must be 0. And since this is a product, we use the product rule. So let's take the derivative of the first term, keep the second one constant, plus, and as you can see, since the inner product is symmetric, we can say 2 times the inner product of the derivative and the curve is equal to 0. And therefore, we have that. And recall the definition of orthogonal vectors. If the inner product between the two is 0, then they're orthogonal. Therefore, the curve and its derivative, they're orthogonal. And that proves this. So it might seem pretty hard to believe, like you can't really, it's hard to visualize, but I guess the math doesn't lie. So let's move on to the second proposition. Let's say we have that gamma is orthogonal to beta, then we have this. And if you looked at the proof for the first one, the proof for the second one might be pretty expected, because let's look at the proof. We start with the knowledge that gamma t, beta t equals 0. Take the derivative of both sides. The derivative of 0 is 0, and the derivative of the left side is that. And if you subtract this from both sides, then you get the desired expression. And furthermore, one consequence of proposition 1 here is that if gamma from I to Rn is a curve with constant speed, then the derivative is orthogonal to the second derivative for all. A quick note, we can simplify the phrase for all into this letter, for all t and I. This is just like mathematical shorthand. And the reason why is because the norm of the derivative is constant, we'll call it c. So that implies that based on the proposition before, the derivative is orthogonal to the second derivative. So that's a little bit about parametrized curves and the inner product. So that's basically all I have for today. Thanks for listening.